At this point, I would like to give you a little bit of an insight of how we can measure these S parameters. So I have a few images here that will help you visualize what happens in an actual RF microwave lab when S parameters need to be measured. Essentially, what we do in the lab is we build instruments that do exactly the conceptual actions that I described before, meaning we launch waves, we take those waves, we hit the network, and we measure the reflection waves, the reflected waves. One of those instruments, probably the most important one that you will see, is called the Vector Network Analyzer, or for short VNA. This Vector Network Analyzer is actually an amazingly important instrument. You will see it in almost every microwave lab. And in today's technology, we can make those type of VNAs launch waves really accurately, anywhere from DC to all the way to 1 terahertz and even beyond that. And so that means we can conduct very wideband measurements. We can essentially characterize a device anywhere from DC to over 1 terahertz by using this type of an instrument. Now, of course, once you launch the wave, then you need to have some way of getting that wave into your network. And the way we do that is that there will always be some cables that will come out of this VNA, and then it will basically take them and connect those to your device. Now, how exactly those cables get connected to your device depends exactly on what type of device you're characterizing. For example, here I have an RFIC chip that you will see right here. This type of an RFIC chip includes very small transmission lines. In this particular case, it may have completer waveguides or microstrip lines, as we've seen before. And so there is some need of a transition. The transition from the coaxial cable that you can see right here to the CPW or microstrip line that may exist on the chip. This type of a transition normally happens through a microwave probe that you will see right here. And these probes are designed really well to make sure that the transition is as effective as possible. So those microwave probes, again, they cover a whole range of frequencies that you can get them or you can design them. And here you can see a close-up picture of exactly this type of a probe. You can see very quickly that here we have gone down to a CPW configuration where this is my center conductor and these are the two ground planes. And on top of that, we have a DC probe that you will see right here. And this DC probe ensures that the right bias voltages are applied on the chip. Now, one of the questions that happens often in life is that none of these things are ideal. Right? So, for example, the cables that we discussed before are not ideal. They introduce some phase shift. They introduce some transmission line loss. This transition from a coax to CPW is also not ideal. But there are ways you can actually de-embed all of these effects. You can check the textbook if you would like to find out more details. There are also excellent tutorials online on the web that you can read about this. It's not the focus of this class to teach you all of those de-embedding techniques. But because we have been doing this for many years, for decades actually, we have now very advanced algorithms and de-embedding techniques that we can essentially take all of these non-ideal effects out of the question and basically make a measurement as if the wave was being launched right here, right at the input of RFIC chip. This is a couple more example pictures that you can see in terms of how measurements happen in real life. Let me start actually with picture C here. So you can see a case where somebody wanted to measure a transistor. So here's a transistor. Obviously, somehow you need to be able to bring the waves to this transistor. So you can see on the left-hand side and on the right-hand side a little wafer that has a CPW line there. And that's the wafer that we will actually connect to our probes. You can basically see the probe connection would happen here or would happen here. And this probe connection can happen either directly or it can happen through another chip. And then we use bond wires, as you will see right here. The de-embedding techniques that I just described also need what's called a calibration standard. So there are specific devices that we use as calibration devices. And those are devices that have very well-known behavior. And the devices that truly have the best well-known behavior in RF is actually a transmission line. So what we normally do is we will make calibration standards, calibration devices that will be different transmission lines of different lengths. These are, for example, 3 through transmission lines. but there will also be transmission lines that may be open or short. So by measuring these transmission lines, essentially then getting the real S parameters measured from this and comparing them to the ideal S parameters you expect from this transmission line, you can essentially de-embed all the effects that I was mentioning before.